Alright, this is Ken Rosever. We're going to talk about central limit theorem. This is my 2010 video. When I originally taught this course in 2009, I explained, I think, the formula, but I don't know that I got really into detail about the why. And having taught this course a few more times since then, I think I'm better equipped to explain that aspect, so I'm going to try to do that here. If we have a population where the mean and standard deviation are known, and we begin taking samples of size n from it with replacement, when we take all the possible samples of size n out of the population, each sample will obviously have its own sample mean, but also the distribution of these sample means will approach a normal distribution as larger and larger samples are taken. Let me go back to some things I said here. So we have a population where the mean and standard deviation are known. We begin pulling samples out of it of a given size. We'll say of a size 10. So let's say I have a bucket of lottery balls that are numbered between 1 and 60, and I begin reaching in and pulling out samples of 10 balls at a time. Now we know there's only so many ways that I can choose a sample of 10 balls with replacement out of 60. Now that's the key. This is, I said with replacement right here. And by that I mean an object, one sample could possibly be reused. So it's not like the lottery where once a ball is used, it's not reused. No, I'm saying I'm taking a ball out, I'm reading the number, I'm putting it back. And I'm going to take out 10. Well, there's only so many ways I can do that. Specifically, because there's 60 balls, and I'm choosing 10, then there are 60 to the 10th possible ways to do that. And that's a big number, 60 to the 10th power. You can imagine it's 6 to the 10 times 10 to the 10th. 10 to the 10th is 10 billion, and then I'm doing 6 to the 10th in front of that. So there's a ton of ways to do that. But if I look at all those and I take the average of every single one of those possible samplings, what I'm saying here is that those averages will be normally distributed, and the average of all those averages will be the average of the population. And you know, if I have balls numbered 1 to 60, my expectation is what? 30.5 is my mean. That's pretty much what I'm saying here. Besides approaching the bell shape, the distribution of sample means will have, for its mean, the mean of the original population. The mean of the original population was, what did I say, 30.5 if I have balls numbered 1 to 60. That is to say, the mean of all possible sample means is still the population mean. However, since we are looking at a distribution of the averages of all possible samplings, the standard deviation for the distribution of sample means will be much smaller. So what I'm saying there, actually it's kind of hard to catch on to what I'm saying there. So what I'm going to do is I'm going to motivate this discussion by way of example. And this is the example I'm going to use. Why is that? Why is it true that the mean for the sample means is equal to the mean of the population, but the standard deviation of the sample means is not? Suppose that I've taught 40 stats classes in my life, and that's not true. I haven't taught 40 stats classes, but suppose I had, and let's say all my classes are the same size. They're all 30, and that nobody drops their ads. Then the average of all my individual student grades must be equal to the average of all my class averages. Let me say that again. So if I've taught 40 stats classes, they're all the same size, the average of all my students' grades must be equal to the average of all my class averages. Now to me this seems obvious. With my classes being the same size, they would all have equal weight. So it makes sense to me that the average of my class averages must be equal to my student averages. But perhaps it's not so obvious to you, so I'm going to demonstrate it to you algebraically for the case of 40 classes of class size 30. So let me get a new piece of paper here. So I want to prove to you that the average of my class averages is equal to the average of all my students. So here we go. I'm going to say let x bar C1 be my class average, and a class is a sample, so I'm going to call it x bar instead of mu. That's my class average for my first class. And I have a lot of classes. Actually, let me do this. So I'll finish off this one and then I'll go down. So if it's my first class that I ever taught in stats, then I would have 30 students in there, and each of those students would have a grade. So the average for that class would be the sum of all their grades divided by 30, or writing it out longhand. And then similarly, for class 2, well, that would be my 31st student up to my 60th student, still divided by 30 because there's 30 students in the class, so I would have S31 plus S32 all the way up to S60 divided by 30. And going down, if I looked at my 40th class, I would have the sum of SIs, and those I's would go from 1171 up to 1200, and expanding that we could write this, and I'll put the dots there, all divided by 30. So all of these would be my class averages. Now if I want the average of my class averages, well then that would be all my class averages would constitute the population, because they would all be all my classes, and there would be the average of my class averages. So I'm using mu of x bar, and I'd have 40 classes, so my index would go from 1 to 40, and it would be of x bars, and then these would be C sub j's. Class 1, class 2, all the way up to class 40, the averages. And I would be dividing that sum by 40. So I would have, expanding that, x bar of C1 plus x bar of C2 plus dot 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 x bar of C39 plus x bar of class number 40. And I've taught 40 classes, so I would divide by 40. Well, now by substitution, I can see that x bar C1 was S1 plus S2 plus da 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 all the way up to S30 divided by 30 plus S31 plus S32 plus dot 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 all the way up to S60 divided by 30 plus, let me skip a few and go all the way to class 40, which was S1171 plus S1172 plus dot 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 S1199 plus S1200, student 1200's grade, all divided by 30. And that's all divided by 40, but another way of saying divided by 40 is times 1 over 40, right? Up here, I could have just gone 1 over 40 times the summation of those XCJs, right? It's the same thing. So now look here, we have all these sums are over 30, and what you should know from arithmetic in middle school is that if you have a bunch of fractions with the same denominator, you can just add the numerators. So I'm going to do that. And when I do, I have S1 plus S2 plus S3 plus dot 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 all the way up to S1115 or 1199 and S1200. And then that's all going to be over 30. And that whole thing will be times 1 over 40. And when we multiply two fractions, we go top times top. This sum times 1 is itself, and bottom times bottom. 30 times 40 is 1200. And so I get the sum of all my students' grades divided by the number of students I've had, which is 1200. 30 times 40 is 1200. And that is just the mean of all my students. Okay? So I've shown that is true, that the mean of the sample means is equal to the population mean. In the next video, I'll continue because I'm out of time.